Okay, well, good morning, everyone. Welcome to EX 151 251A, Introduction to Digital Design and Integrated Circuit. Let me see whether I can close this. Okay, perfect. Okay, we get to our, sixth lecture of this semester. We're going to wrap up combinational logic, more focusing on how we can actually do more simplification to get a simpler circuit, and we'll also get started on the finite state machine. Before we get there, I guess the news of the week is Apple's new SoC, the A19 SoC that will be used for the iPhone 17 family, right? So as many folks probably know, Apple has been actually very regularly, I guess, over the past decade in actually releasing a new generation of SoCs every year. And this is their latest generation of SoC. I guess we still don't have the real hardware yet. We'll need to wait until the iPhone 17 release. So we only have this kind of very high level diagram, but it has been really interesting to see the evolution of Apple SoC, and in particular, actually how things have changed. Apple's SoC has been a very good representation of this kind of different heterogeneous SoC that we observe, especially in the mobile market. We talk about this kind of big GPUs and scale up, scale out, even scale across. But if you look at this kind of consumer electronics, a very typical architecture that we have been observing over the past really decades or two, really this kind of more heterogeneous SoC. So whenever you see Apple's SoC, it always have a mix of different components, right? So there are different CPUs, like big CPU cores. There are like four, they call it energy efficient E cores. Those are like smaller CPUs. And those are, anyone have a guess? What are those big things over there? It has been the source of Apple's SoC improvement. RAM. Well, there are lots of RAMs there. That's a good guess. But what is like functionality? It's actually taking very big over generation SoC, and that has been marketed as a source of improvement, the biggest source of improvement across generations of Apple SoC. It is pretty close. Those are here. Yes, so here are neural network NPUs here. Also, this is not a real die shot, right? This is just a diagram. We don't know exactly what the hardware look like, but it's a pretty cool illustration. And this is a GPU. So Apple's GPU actually getting bigger and bigger over the past generation. We're very excited. Well, I guess we're looking forward to see the real die shot to see how big they are. But that specifically has been marketed as a biggest source of improvement. And in particular, this generation GPU, they added more ML functionality. Anyone have a guess? Tenzi? No? Oh, yeah, I thought you were like Apple fan. They labeled as there are big squares over there. So they say the 5-core GPU, and they're like big squares over there. It's for ML. Anyone has a guess what they are now? Adam?
I was thinking tensor cores, but those would go on the NPU, right?
Well, that's a good question. Yeah, like whenever I think about ML, right, tensor cores, they already have NPUs, right? But it's actually a very good guess. It is tensor cores, or they are adding mathematical engines, actually all even inside GPUs. They are also, yes. So those are what I labeled are tensor cores, and another special flavor of GPUs are actually accelerators are ray tracing cores. I guess NVIDIA pioneered that, and now all the GPU vendors also adding that. So if you look at the ML hardware landscape, even on a like small SoC, or like Apple's SoC, pretty decent, right? We see actually different flavor. There are like GPUs adding this kind of mathematical engine for machine learning these days. NPU, as we discussed, right? They are designed for neural processing, right? So they are also designed for machine learning. We don't know the exact detail yet, but at least for A18, which is a prior generation of Apple's SoC, even for those CPU cluster, they are having actually generations of what they call, I guess, used to call AMX, Advanced Matrix Engine, because now it's being unified under ARM's SME is like streaming MACMO, and so even in the CPU cluster, there are also dedicated MACMO engine, also for machine learning, right? So it's actually getting very interesting, even for this kind of, given how machine learning is like popularly used in a lot of different scenarios, we are seeing, of course, it's heterogeneous here, CPU, GPU, NPUs, and there are like generations improvement in each of the processing element, but also they are equipped with more ML capabilities in really thinking about how we can actually accelerate ML more systematically. So very interesting trend. Again, this is not, it's just an illustration. We're looking forward to see the dipole. If you search online, you can actually find A18, the prior generation of the dipole, and then you can see roughly how things are or size. But one thing in particular, GPU actually get bigger and bigger. Anything else interesting in the announcement? Oh, here. So with access to TSMC's latest 3-nanometer generation technology, right? So we talked about earlier, getting the latest generation technology actually very important, and Apple is always the one who actually have access to TSMC's latest generation, right? So this is a 3-nanometer generation. Anyone has a guess? What's A18? What's the technology they were using? Huh? 5 is a good guess, but we're talking about things are slowing down, right? So they mentioned this latest 3, right? How many variations of 3 these days?
3.
Yeah, so A18 was actually using N3E. It's like one. So they're doing this, getting really hard to actually get very significant boost across generation and the generations, or they're doing a lot more fine tuning. I'm actually also losing track of the exact name. This, I think, is actually N3P. It's like more performant one. They can actually get to roughly like 5 to 10% performance boost. So that's like the way they're getting the cadence now, but it's actually not a big enough jump compared to generation to generation. So even for we talk about like the slowdown of Moore's law, it's getting really expensive and competitive to get to actually more advanced technology node, right? Even for someone as resourceful as Apple, who actually has great collaboration with TSMC, is also getting harder to advance. So now generation to generation, we're actually observing the slowdown. It's still better. It's still better than the prior generation. We're looking forward to see the spec, right? So far, it's only cartoons from the announcement. It'll be interesting to compare how those, I guess, more mature generation technology, how they actually advance and differ from each other. Right, so a lot of interesting announcement. We'll keep an eye on what exactly A19 looks like. And for folks who are interested, there are actually a very interesting die shot. People are actually analyzing A18, and you can see actually the more representative sizing of different components. So this is, I guess, Apple, some of the more recent interesting news on the state-of-art SoCs, especially for consumer electronics. And we already see this heterogeneity, the different components, the relative slowing down of Moore's law and getting harder to actually have the leading edge technology, and also how important ML is in across different platforms, as a lot of different components are actually being added in accelerating ML. So with that, a quick recap of what we discussed last lecture. We started talking about combinational logic, talk about the importance of actually doing more efficient implementation and using Boolean algebra as a way to do simplification, right? For homework this week, you folks will play with different Boolean expressions and see how you can actually get the simplified logic. For today's lecture, we're going to talk a little bit more. It's actually a pretty cool way of doing more simplification by hand. You can actually see how you can actually get a more lean version of the logic, but actually implement the same functionality. But before we talk about the specific techniques, right, it's still important to review why we actually care about simplification, either with a Boolean expression or with a kernel map that we're going to introduce in a minute. Overall, you will see the intention at a very, very high level, at a very abstract level. We want to minimize the number of gates in circuit, right? Why it matters? It's because like everything's very physical, right? In the design process, when you actually put more hardware, more components on your silicon, it takes area, right? So here we're using the number of gates as a proxy, thinking about area optimization, right? Getting to a lower cost. And also another dimensions, when we actually have simpler logic, we can also get actually relatively simpler wires, right? If we look at like the die shot, it's not the die, it's really a diagram, we'll see different die shots. The die is actually getting bigger. There'll be a lot of long wires here and there. When you have a lot of gates, you actually need to connect them together. And we'll talk about timing, right? We'll get to like different logic timing. We'll also talk about wire timing. It also takes time to actually propagate signal from one end of the chip to the other end, right? So when we actually can cut the number of gates actually needed for the implementation, we can also cut the wire cost. And overall, we talk about area, but when you have smaller number of gates, we talk about it takes time to propagate, right? When you have fewer gates on your critical path, your circuit can also get faster. And typically, the EDA tools are actually getting very good at doing logic simplification. A lot of like this kind of high-level concept that we're introducing, they're like over decades of different algorithms are doing this kind of simplification. But it's still important to understand why it matters and also understand some of the early days, right? When we don't have this kind of more automatic tools, how people are actually doing some of the optimization by hand, just understanding what are the underlying principles. So a lot of concepts that we're introducing here, I don't think it's really dated per se. The specific techniques may or may not actually appear in modern EDA tools, but it's really, really important to think about principles, right? Why people care about that before we have those modern EDA tools, how people, for some very simple design, how people are doing this kind of optimization by hand so that they can get a like simpler and also cleaner version of the design. So with that, when we actually think about the way we apply Boolean algebra, right? So we talk about their different laws here. And in particular, one theorem is actually very important, is I guess what we call the uniting theorem. But basically, you can actually simplify the term, actually cut one variable of the term. So if we are seeing a pattern, we're actually have one variable that either end with a negated version of the variable and or with the original variable, we can actually extract x here. And what we eventually get is that y actually doesn't really matter, right? So the entire equation, the entire expression is really only dependent on one of the variable instead of two. If you look at the truth table, it's a little bit easier to see that, right? So again, we talk about to do actually find the number of cases, rows when f is true. And we get here, even when we actually have both A and B as input, right? We see here, no matter what B is, it doesn't really matter. It really only depends on one of the variable. So this is a very effective way of cutting the redundant variables in the design and potentially get a both smaller number of gates and even for the same number of gates, smaller number of inputs, right? You don't need to actually consider all the inputs. And this is a very powerful way to eliminate unnecessary inputs and actually get to a very good, a better output. So we can certainly do this by hand, right? When you actually applying Boolean theorem to do optimization, you will see this actually come in pretty handy in a lot of cases, right? So one of the example, let's see, we want to do the carry signal of our full adder, right? We talk about our full adder. We have A, we have B, we have the carry in from the previous stage. And when we do a full adder, we have result and we have carry out, right? So that's our full adder design. As we discussed, we can actually write the truth table very easily to express the relationship, right? But now let's see, we want to do the carry out. Carry out, we find the rows that where carry out is true, and then we can actually writing the expression. So now we write this kind of sum of product form, a form of all those expressions, right? We talk about how we can potentially eliminate actually inputs when we see the patterns where a shared component is actually ORed with both the original component and also the complemented component, right? What are some of the patterns here? For example, here, A and B is AND with both C bar and C, right? So whenever we see this pattern, it basically means C doesn't matter, right? No matter whether C is true or false, it is always lead to the same output. So this is a good opportunity to actually eliminate C, and you get a simpler version A and B. You can do this multiple times, right? And you see this for this term, you can actually bring this clean version again. So here you can also write it multiple times. It actually doesn't change the output of the values of the expression, right? As long as this is true, right? So here you will actually combine this term again. We see very similar patterns. A and C stay the same, but B has both B bar and B here. So basic means it doesn't matter with B, right? So you get A and C here. And we can do this trick again with this, and you get B and C, right? So this is a very powerful way of eliminating unnecessary inputs that actually doesn't change the output, right? And then when you actually start with like more many 3 input gates, and eventually you just get a smaller number of both you have smaller number of gates, and all of them are only 2 inputs, right? Does this make sense? Very high level, how we actually repeatedly apply this, right? We're not going to go through this in details, but I did write down a more step-by-step way of actually doing this. So this is a way of, I guess, applying this theorem to actually get a simplified circuit, right? But here we're writing a lot of equations. It's very error-prone, and there are like so many different steps. When people actually approach this, they're wondering, we are, again, a lot of assumptions here that we're doing this by hand, right? We're talking about people in the 50s who just started thinking about circuit design, and they try to understand how to get a simplified circuit, right? It's very annoying to write those equations and thinking about how to apply it. So back then people are thinking about, oh, this is basically patterns, right? We're finding patterns where there are this kind of shared component, and then we have complement and original component together. Is there a way to better visualize it so that it's easier to do this, to apply this principle to all the different circuits? That's basically when people start doing kernel map. This is, again, a way of thinking about logic simplification. It's following the same principle as what we introduced for the Boolean algebra. But here, this is a more visualized way of actually using, we'll talk a little bit more, this kind of particular map, and it's actually much easier to apply this principle to find a simplified circuit. What's really kernel map, right? So you can really think about this as another way of a visualized truth table. It has the same information as truth table, but it's easier to identify opportunities that you can actually eliminate, like the component that actually doesn't matter for the expression. So here, let's say this is an OR gate. We start of the truth table. And what kernel map really is basically another way of using the truth table. We talk about, for truth table, we have input and output. Here we have input as a row or column indices, right? So input and different inputs are just how we actually index a particular cell. And the output is actually being populated in the table or in the map, right? So the entries of this map is basically the output, right? So here we're filling the map with values from the truth table. So the input are used as indices, either row or column indices. The output are entries of the truth table. So here, the key optimization, remember what we did here for the carry case, right? We basically, in this particular case, we basically find opportunities to eliminate, right? The components, they actually don't matter. No matter whether they're 0 or 1, it's always 1. So we can do actually very similar things in a more visualized way with kernel map. So here, when we actually populate this OR gate, we mentioned we use A and B as row and column indices, and we populate the entries, the value of F as entries of the kernel map, right? So here, what we are actually looking forward to is actually do the logic simplification so that we don't actually need to write each term of each row. Where F is 1, we can find opportunities to combine them together to get a simplified version, right? One way to do that is doing the same way as the uniting theorem is actually just by circles group of ones together so that they can be eliminated. What do I mean by that, right? So here, let's say for this column, when A is 1, I see this patterns where group of ones, these circles are actually adjacent to each other across different rows. What this basically means is as long as A is 1, no matter what the value of the B, the output is always 1. Does that make sense? Right? So if I have my particular row, a column fixed, it doesn't really matter what the row index is, right? It's basically only determined by the column. So with this, I can basically write one component of my equation expression, right? So it doesn't really matter when, as long as A is 1, A is true, the answer, the expression is true. Right? Does it make sense? Which is the same way as applying the uniting theorem we did before, eliminating B. And we can do this with another agent. So we're basically circling this group of ones that are adjacent to each other. So we can do another circling here, and it's okay to share, right? To reuse this element exactly as what we did with a carry out expression, right? If this is true, we can actually reuse it as many times as possible so that it helps us to eliminate the term. So here for this circle, as long as B is true, right? So as long as it doesn't really matter whether A is true or false, right? So if you write it in equation, you'll write down step by step to actually simplify it. And here is a more visualized way showing, okay, as long as B is true, we're in this row, and it really doesn't really matter what the value of A. So then I can eliminate A in this scenario and only write down B. Right? So here we can have a very easy to approach visual way to perform Boolean simplification following the same step, but it's just visually it's more approachable. It's easier to think about steps instead of actually looking for equations to actually apply. Does this make sense? A very high level what kernel map is trying to do? Right, so it's basically, as we discussed, converting the truth table into the kernel map. Output is in the cells, and input are used to index the cells. What we're step by step, we're basically forming group of ones across adjacent cells. I remember the uniting theorem, right? It's always a pair of two. It can be bigger, right? We can actually eliminate more terms, but it's always a pair of two so that we can actually eliminate the terms that are basically complementary to each other. With this, we can actually write down a shortened version of the term so that it's actually after the optimization. And then we can actually form the sum of product way. So we're still doing sum of product, but all the redundant forms are actually eliminated. And clearly this is an OR gate from the truth table. So we're again doing the truth table to actually, to Boolean expression conversion, but we're actually doing things in a more effective way without repeatedly applying the Boolean expression here. Does it make sense? Very high level what we're trying to do is kernel map, right? It's just it's cool techniques people invented, I guess, at this time, at this part as more than 5-6 decades ago, but it's like very effective and it's a very visual way to think about simplification. Just a little bit more examples, as we discussed, is another way of thinking about truth table. And truth table is always across rows. A little bit hard to find the patterns, but now we actually want to a more like visual way to find the adjacent term that share a group of ones, and then we can eliminate those together, right? So this can be multi-dimensional. We talk about for two input, it's very easy, right? One input is a row index, one input is a column index, right? But when we have like 3 input, we can still do that in a fairly effective way, right? So you can actually combine like 2 of the inputs together as a shared indices and have another index here, right? One thing in particular, I guess worth noticing is that when we actually have more than one index, when we actually encode the table, encode the entries, we like to do what we call gray code labeling, basically for every adjacent adjacent element, there is only one bit that is different from each other. Why is that matters when we actually do the elimination? Why do we want to actually use gray code here? Only one bit is different from each other. Any? Right, simplifies the logic operation, right? In particular, very importantly, we mentioned we want to find the term that only one bit, one input that's different from each other, right? So here, by using gray coding, we can actually make sure, in this particular case, B stays the same, but A is actually the original, like the 0 and 1. A is actually complement with the two different cells, right? So here we can actually apply simplification to eliminate one variable. You don't want to have two variables changing simultaneously, then you cannot do the elimination, right? So very importantly, when you get more than one variable, we're actually using gray code so that we can actually eliminate one variable while the other variable is shared across the adjacent cell. And we do the same thing for the other indices, right? So always one bit stays the same and only the other bit is changing. All right, so here, I guess we can actually see examples. Let's see a couple examples, just get a feeling of this, right? So let's say we start with two input, right? Just A and B and A0. So we don't need to worry about gray coding, right? Just like two different elements. And here we actually, again, we get this, we start from truth table, we convert it into the cardinal map. The first thing we do is to find group of ones across adjacent cell that can be actually eliminated, right? So here, what we can find is that here, we spot two ones that are adjacent to each other across rows. And here for this, it's basically as long as row index is 1, basically means as long as A is 1, it doesn't matter what B is, right? So here for this gate, for this expression, what is F? F is basically A, right? It doesn't really matter. So that's how we actually do simplification. As long as A is true, F is true, right? We'll just do another example very quickly. Still two variables. Here, A and the B. Again, we get the cardinal map and we start circling group of ones, right? So here, what we find is as long as B is 0, and no matter what the value is A, it's always 1. So this gate is not B, right? So because it doesn't really matter the value of A, right? As long as B is 0, so it's basically an inverter. So we can also do this for 3 input, right? So we have A and B and the C. And notice we always, when we do the more than one variable, we use gray coding so that only one bit is changing. So what we can do here, we start again circling once. So here, the first circle is basic as long as A and B is 1, it doesn't really matter what C is, right? So that's very similar to what we did when we do the Boolean elimination, right? As long as for this group, as long as A and B is 1, C doesn't matter, right? So that we get a simplified term. So let's keep going. There are more ones in this table. Let's see, there is another one here, right? So for this, you see why we actually want to use gray coding here, because only one term is different. So here, for the blue one, both B is always 1 for the two entries circled by the blue circle. C is always 1 here. The only thing different is A, right? We have both A is 0 and A is 1. It basically doesn't matter what the value of A. This is always true. So this means it's basically, this is only dependent on B and the C. So that's how we get the second term. We'll keep practicing this. We see another circle here. So circle here is basically, for this design, A is always 1, C is also always 1, and it doesn't really matter what the value of B. So here we get the last term, A and the C. Right, so this is how we actually do step by step, basically doing the same thing as we try to eliminate the term. And as long as we find the condition, it means the term doesn't really matter, we can eliminate that. So again, we start from a more complex gate, get and this is the same one as we did for the full adder carry out signal, right? We can again apply in Boolean equations step by step, but we can also do this more effectively and more visually using this kernel map. Kenzie? The first one, so let me change my color. So for the first one, what I'm circling is this circle, the circles in red. Right? For the circle in red, basically, as long as I'm in this column, it doesn't matter what my row index, what the value of C is, right? So if C is 0, it is 1. If C is 1, it is still 1, right? That basically means I can eliminate C because C doesn't matter. And for this particular entry, it basically means when A and B are both true, this is true. It's the same principle here, but it just instead of, I guess, here the column index is only one variable, here the column index is two variable, right? And you can always think this is basically doing, you have A, B, C bar and A, B, C for this column. And if you do this with Boolean expression, you can eliminate the C bar here. And that's basically exactly what we are doing here. Just a more visual way to do that. If you write down the term. Sure.
Is like form a group of 4 blocks, basically, but it's not a square.
Oh, you mean for this one? Yeah, yeah, so it's always the power of 2 because you actually want to do elimination. So that you remember the uniting theorem is basically only one, but you have 2 terms, and if one term is basically complementary to each other, inside the term, it can be eliminated, right? So you always look for the power of 2. But you can reuse, right? So you can certainly reuse the term to actually form more circles to be eliminated. So but you can, let's spend a little bit of time on this one, right? So this one is interesting as it can actually circle more terms. You actually want to circle more terms, right? The more term you circle, basically means you can eliminate more input. The basic more input doesn't really matter here, right? So for this term, you will look at common variable, right? So here, if you compare the column indices here, right? It basically means it doesn't matter whether B is 1 or 0. This is always true, as long as A is true, right? And if you look at the row column here, it basically says it doesn't matter whether C is true or false, the term is always true. So when you actually get to a bigger circle, you can eliminate more term. So in this case, if we actually get this full circle, and we basically get B doesn't matter if we actually compare the different columns. C also doesn't matter if we actually compare different rows. So the output of this truth table, this gate is just A, right? It doesn't really matter. It doesn't matter what B is. It doesn't matter what the C is. So now if you draw a bigger circle, you actually get eliminate more term, right? So if you draw a circle with 2 elements, you can eliminate 1 term. If you draw a circle with 4 elements, you can actually eliminate 2 terms. So you can actually get to the essence of what the gate really is. Question?
Well, given like a certain logic, and there are when there are more variables, there are different ways to arrange the rows and columns. Are some arrangement like easier than others, or on the second, or we just got like a better?
Yeah. That will be a good exercise to try, just to try whether you put rows or column for different variables. The answer is you will always get the same thing, as long as you follow the gray coding, what we mentioned earlier, right? Only one element that is different from each other.
Yeah, what the groupings of 0 represent that?
Oh, that's a good question. So far we have been talking about group of ones, right? Even in this example, you also see you can also see group of 0. We'll get back to that in a minute. Just a little bit more on this. People design really fancy things, especially in the 50s and 60s when they actually need to do a lot of manual manipulation. So we talk about the 4-dimensional so that you can still visualize this, like on paper in a 2D plane. People design very fancy things with this kind of 5-term, 6-term, it's become 3D. If you're interested, feel free to play with it. You can also eliminate across different panels there. Again, finding only one term that are different from each other. It is out of the scope for this class. We will never test you. I don't think people even in interviews will actually ask you questions like this. Given this, again, this is just a more understanding the principles of logic simplification. A lot of things are actually really taken care of by the tools, but it's pretty cool if you're just curious how people actually do simplification by hand in old days, and how things actually would work when you get more terms, and how you actually draw weird circles across panels. Feel free to try that out. So you can also go deeper. But after, I guess, even 5 term is also getting a little bit hairy there. Unless you're really interested, I wouldn't suggest you to go even further, but that's something fun to play with. And we talk about, I guess, how we actually group ones, and that's basically one of the most common ways you do actually the simplification, where you can actually get a sum of products similar to what we discussed, the way we express a Boolean expression earlier. But your name is?
Oh, Emerson.
Emerson, right? Emerson mentioned sometimes it might actually be easier to do zeros instead of ones, right? So for this example, you see we have a lot of ones, right? We actually start eliminating for ones. There's like just a lot of terms that you need to care about. What you can do is you can also circle zeros, and then it's basically complementary to the way we actually do circling ones, and then instead of the sum of product term, you will actually get a product of sum term. I won't go through this. This is also something fun. Feel free to try it. But this is one thing interesting. Just keep in mind, we haven't seen this pattern before, but looking at the adjacency, right? So this is also an adjacent term, right? So you will see this, they are the same row. So the row index doesn't change. And for column here, right, in this particular example, B stays the same and A is only one that is actually complement to each other. So this is also a valid circle that you can also try to eliminate when you do optimization. So this is another way, depends on you have more ones or more zeros. That's basically you can convert from sum of product to product of sum. So here, just a quick recap. We talk about combinational logic. Again, the key part is the output only dependent on the current value of the input, right? We don't have state. We'll talk about the state specification later, right? So then we talk about how you can actually choose table. You can always start from choose table to exhaustively list all the potential combinations. And it has been actually pretty useful to think about applying Boolean algebra to do the simplification. And one thing that is really cool, it's always fun to play with kernel map, even though it's like a stated in a way, but it's like something you can still comprehend, and you can actually still see the power of logic minimization and doing things by hand. That's how people actually get started when they actually need to design things. Again, when I was a student, kernel map was a very common interview questions. We'll see whether you folks run into kernel. I would be very surprised, but I think that's still a possibility. Question?
So we've been talking a lot about minimization in this, but is there like scenarios the maps where you have like maybe like some weird like A, B prime, C plus A, something like that? So you need to like expand the actual Boolean representation?
Yeah. So that's a good question, right? We always talk about using Boolean expression to get the smaller number of gates as possible. Again, it is just a proxy of area and the timing, right? And there are some like different technology may have very weird trade-off. It may not be always better to have like smaller number of gates compared to maybe more parallel gates or different ways of organizing things. So again, we are only using the number of gates as a proxy because we don't like get into the whole like physical design process, but that entire process could actually change the trade-off, right? The smallest number of gates may not be actually the most optimal design when you so you may actually want to expand, you have more gates, but maybe fewer number of inputs. That's actually a much bigger trade-off. A lot of EDA tools are actually doing there. Good questions. Okay, with that, let's see a couple announcements. I hope lab 2 is going well. I got some feedback earlier. Keep us posted on how things work. We understand. I think lab is always very challenging, especially early on. You want to have a little bit more staff time so you can do checkoff and also ask questions. But also there are also a lot of things going on. We still encourage you folks to attend lab. It's very important to get to know each other and also work together to form a community. We have different ways of organizing our staff. We're also trying different ways. So hopefully that could alleviate a little bit lab pressure, but also let us know what works, what doesn't, so that we can also be more adaptive in the way we run the labs. And definitely very importantly, don't fall behind. Things will be accelerated very, very quickly, starting lab 3, in particular lab 4 and 5. Those are actually very, very substantial. Those lab 2 is really just to warm up, right? So get it done on time so that you can actually focus on the later part of the lab. Lab 3 starts this week. Lab 3 already started intensifying a little bit. You're doing something a little bit more substantial, so don't fall behind. And we have, I guess, homework 2 due this week, and we'll release a new homework for cover, I guess, this past week for homework 3. And homework should be very straightforward. Again, it's just a mechanism to force you and encourage you to review the material, but they shouldn't take too much time as long as you are following lectures and discussions. Heidi? So update on the waitlist. So where I see things are moving, I notice a couple folks on the waitlist are progressing. So those are good news. At this point, I'm optimistic. So lecture doesn't have a waitlist. We will enroll anyone that is enrolled in the lab. It will be automatic enrolled in lecture. So lecture doesn't have a waitlist. For labs, I think things are moving. I'm very optimistic for folks on the FPGA lab. Things would be cleared soon. Are you still on the wait list or are you? Oh, okay. I'm optimistic about FPGAs just looking at how things are moving. ASIC lab, I would say at this point, if you're not position 1, you should start looking for alternative option, just given the waitlist is pretty long, and I think we are basically limited by the lab capacity at this point. It's going to be very challenging to move, to absorb the ASIC waitlist. Question? I'm also really, really curious because I also need to finalize my schedule. So currently it's basically blocked by finding the room. So it's out of our control. Department staff is, so we're working with the department staff to finalize a room that can host everyone. We can only see that week. I think mid-October, that is a week we told the department staff we can accommodate any day of that week. We're just waiting to see which room. So it's out of my, I also really want to know what's the, but it will be that week, and we know that for sure. Any other questions? Is there extension? It will be a case by case base. I think there is an extension form you can submit, and our staff will review. So if you have any scenarios or things like people are on the interviews or like conflict, we understand things happen, just submit and we'll review that. It will be a case by case base. Okay, well, keep us posted. This is on enrollment. I just checked the wait list. This is my update. I tried my best to modulate. I think the wait list is not progressing as like, I guess that's a good news. Most folks actually stay in the class, so things are not moving that fast. So yeah, I'm optimistic at FPGA lab, given the waitlist is pretty short. But for ASIC lab, again, if you're not position 1 at this point, definitely start looking for alternative ways to get enough credits for the semester. Yeah. Okay, great. That's all we have on the announcement side. I guess with that, we wrap up. We'll conclude it, combinational logic. For the discussion, you will see this class will talk about layers of things. We'll just keep talking combinational logic, sequential logic, different elements. We'll come back again, actually, how we actually use transistors and basic building blocks to build different flavors of combinational and sequential logic. So you will see the layers of abstraction we're going through. But for the current layer in thinking about design, we wrap up, I guess, the combinational logic part. We'll get to the sequential logic part. And the best way to think about sequential logic is using a finite state machine and thinking about how our circuit are transitioning across different states that is memorized by the state element in our hardware. So just a quick recap, we have been talking about fundamental building blocks of hardware, digital hardware, sequential logic, and combinational logic. We mentioned combinational logic is basically output only depends on the input. There are no states. But for sequential logic, where is memory, right? There is a state component that actually remember in some way what happened has been accumulated in the past. So there is a state here. So the output of sequential logic is a combination of both the input and also the state element, right? So that's basically the gist of sequential logic. The output depends both the current value as a current input and also in some form of previous value that has been accumulated as a state element that has been memorized in our hardware, right? So here when we think about state, right, that's basically like the information that been accumulated or in some way projected into the state element to remember what has happened in the past, and typically stored in flip-flop or registers. That's basic for most of the discussion we can think about. Those are the state elements actually being used. A finite state machine is a very useful way of thinking about how we approach sequential circuit, right? So basically, we have output that dependent both on present input and the past input that are being stored in the state element. We'll first start how we actually design this by hand, and hopefully when we get to next lecture, we'll talk about how you can actually implement this in Verilog, and that will be how you design your labs and how you do the design in your lab and how you do the final project. So a little bit more about how we think about state machines, right? Finite state machines, basically, again, we're talking about sequential circuit. Whenever we talk about state, right, it has to be sequential circuit. And there are three important components. We always have input, right? So here are the inputs as actually being fed into my sequential circuit. And then I have output, right? Those are output that propagate to the next stage, to the next sequential element, to the downstream circuit about the output. And inside, as a sequential logic, a sequential circuit, I have my state element that remembers, accumulate what has happened, and that will be my inside state, right? So when we actually think about sequential circuit, always those three elements. And fundamentally, when you actually think about how you realize that, how this kind of things being materialized in hardware, it always includes, of course, you need a state register, right? The register, we talk about, those are the memory elements, flip-flops, that are actually store the current states. But then you also need to have combination logic. You still need to have the logic component to help you to determine how you actually propagate input to output. In particular, there are two things will be actually more merged together when you actually get to the design part, but just from a principle part, what are the different transitions actually going on, right? There are also two parts of the combinational logic. One is really to determine what are the next states, right? That's a state transition. That the first part of the combinational logic takes the current state, takes the present state, and takes the input, and to determine what are the output, right? Those are the external visible outputs, and you need to have way to process that. And this will be the circuit to process to how to get to, so first is how to process to get to the next state so that I can update. And what I discussed earlier is another combinational logic is how I process it to actually get to the output, right? So here, again, when we think about sequential element, sequential circuit, I, of course, need to have the flip-flop or state element to remember where I'm currently is, what has happened, right? But then you need another two circuit component. The first one is to guide me I need to go somewhere else, right? The input is being projected to my state. How I go to the next state, right? I need to accumulate the next. That is the first combinational logic for some computation going on. The second combination logic is how do I actually propagate my input to output to tell the downstream circuit what to do next, right? So that's the combinational logic to take. There are different ways to think about this combinational logic, but the end goal is to actually produce the output to actually go to the downstream circuit. So that's three very important elements of any sequential logic. You need to have state element to remember the states, and combinational logic to both calculate where my next state is so that I can go to the next state, and where my output is so that I can reflect things that I have done to the downstream circuit. So those are the three elements in sequential logic. So let's take a look at example. This is probably a very simple example I put together a few years ago. Let's do a very simple cat brain example. You have a cute cat, right? We talk about, if you think about finite state machines, now we have a very simplified cat brain. It has some states, very simple states. This cat is very naive, right? So it's basically eating, sleeping, and very easily. It also can get very annoyed. Right? What are the inputs? How humans are interact with the cat, right? So you either feed her or actually pet her, or what are the outputs? What are some of the signals that's visible for the external component, right? So for this cat, it's basically, let's say, eyes, whether it's open, they're open or not, or the mouth, whether they want to eat more or not. I was preparing for this lecture. I was like, oh, this is such a cute cat. And now I look at my current cat. That's how things have progressed in 7 years. It's a very big cat at this point, and not very interested in human. It's happy, right? So let's see for this cat, right? How we actually think about the cat brain as a way of representing a finite state machine, and how we get inputs and outputs propagated go through this finite state machine, right? So first we talk about here, one thing with finite state machine, I assume you folks have seen earlier version of that in 61C already, right? So with that, again, we have circles to represent the states, right? So here, let's say, the cat is in the eating state, right? So here a circle represents a state that we actually stored. And for output, it typically depends on the different flavors of the states. It can be either labeled in each state. So here in this example, it's labeled in each state, whether eyes are open, true or false, or whether mouths are open, true or false. Or it can also go to arc. We'll do an example about that later. But inputs are always in arcs, right? So whenever we feed that, we talk about how my input actually change or disturb the state of the machine, right? So here it's already eating, and I want to feed more. It's staying in the eating state. But it's eating, and I start patting. It may get sleepy. It get to the sleep state. So this is another state in circle. In a different state, it may have different output, right? So the eyes are closed, and the mouth is also closed. I keep feeding. It doesn't matter. But now I start patting. I may wake him up, and then he's a little bit annoyed, and that's another state. And then gets different input. You will actually have different output. And this is basically a state transition and diagram, right? Again, the state is in the circles to represent where the machine's current state. And then you have input. And input may actually disturb the current state. You may actually stay in the current state or go to the next state, right? So this is a very simple state diagram. And for this particular machine, their output, what's externally visible, the output is dependent on current state, right? If it's eating, the eyes are open. If sleeping, the eyes are closed, right? I'll see you in a minute. This is a representation of Moore's finite state machine. So how do we actually start from this kind of very high level abstraction, get down to hardware implementation? So here we basically, we talk about truth table, right? We want to figure out, we have state element, we have combinational logic that will tell us how we do state transition and how we do output, right? When we think about combination logic, we want to understand what are the input, what are the output, right? So, and we want to have a truth table to actually tell us how states are transitioned, right? So you can think about this as basically a truth table for next state, right? Where we have the current state, we have another input. Those will help us to determine what the next state of the FSM is, right? So it's basically describing, converting this diagram into this truth table representing the state transition, right? So for example, we start with the eating state, right? And we keep eating, we are in the feeding mode, we stay. The next state is the same as the current state. But if it's already in the eating mode and we start petting the cat and the cat will go to the sleep mode, right? So that's basically the state transition will get to the next state, right? So here is basically a truth table expressing from this state diagram into the truth table expressing how my next state will be progressed based on my current state and my current input. Right, so here is a symbolic table. I'm doing this slowly, but you can actually quickly have a way of encoding the different state, right? So here is a very simple binary encoding, and then for both the current state and the input, and then this will more like a truth table you folks are very familiar with, right? You have the input, you have the output, you have a bunch of zeros and ones indicating what are the current states are, what are the inputs, and what are the outputs, right? Once you have that, everything is basically what we have covered before. You have a truth table, you can start doing minimization, either using Boolean expression or kernel map we just covered, but now we get a way to actually start from state transition diagram of like what are the different states, how they actually transition from each other, combine with a unique encoding that you like to use, and then get to a truth table to express the next state, and then let's get to a simplified expression about how my next state is actually covered here, right? So remember, we think about sequential logic state, right? That's always a state element. I need a flip-flop to remember the state. There are two combinational logic, one combinational logic to calculate where my next state is, right? Based on the current state and input, where my next state is. So this is the first part of the combinational logic. The second part of the combinational logic is determine what is output that is actually visible to the external downstream circuit. So with that, that's basically the output part we haven't discussed earlier, right? The output, it also, we talk about it depends on the current state, right? In the eating state, my externally visible output is whether my eyes are open or not, whether my mouth is open or not, right? We can do the same state encoding. And here we get another truth table, like basically labeling whether expressing how my output actually change based on the current state. And again, from truth table to the simplified logic expression is what we have covered, right? There are a lot of ways to do simplification. You folks are very familiar with that. But the key part is thinking from this kind of high-level symbolic logic transition with the encoding, eventually get a form of truth table to express how my next state transitions with my current state from my current state and input, how my output transitions from my current state and input. That things make sense? Just very high level, how we go from this state transition diagram to this more specific implementation. So again, once we have the Boolean expression, right, and then you can actually get to a gate level representation. And here is how we actually calculate the next state. And here is how we calculate the output, right? So at very high level, this is a combinational logic. Let's say the second combinational logic to calculate the output. Here is what we talk about, the first combinational logic to calculate the next state based on the current state. And here is my state element, my flip-flop that I actually used to store the state, right? So here are how the different pieces are connected together when we think about how to construct a sequential circuit. I think makes sense so far? Okay, so here, if we just a quick recap about the step we have taken, right? When we think about sequential design process, right? We want to understand the circuit function, want to basically draw the state transition diagram to understand how states are actually transitioned from my current state to the next state, and also from the state to output based on input, right? It's always handy to just write down the symbolic transition table, and then you can actually get to an encoded one. We talk about do a binary encoding, what we discussed earlier. Sometimes you can also do one-hot encoding, depending on the different inputs that you have. Once you have this encoded transition table, this is basically just a truth table. And then you can do the typical simplification, everything we discussed before, and we'll talk about how you actually construct it in Verilog next lecture. But after that, it's basically how you get combinational circuit that to calculate both the next state and the output. And eventually, again, what we arrived is we have registers to hold the states, remember where we are, and also we have combinational logic to, again, always figure out where I should be in the next clock cycle, in the next state, and what my outputs should be. Okay, just a very high level way of thinking about finite state machine. That things make sense so far, so good. Again, always three elements, state elements to store the states, combination logic to calculate, figure out next state, and a combination logic to figure out output. So this is very high level. When we think about FSM, we already hinted a little bit, right? For the cat example, it's basically whenever it's in eating state, the output basically represent where the is associated with where the state is. And typically when we think about hardware FSM, there are two flavors FSM. You folks probably have seen that earlier. Typically we mentioned three elements, right? State element, combinational logic calculates the next state, and combinational logic calculates the output, right? For the next state, it's always clear, right? It's always determined by where I'm currently at, and also the current input that will tell me where I want to go next. But here for the other combinational logic, where I actually want to produce output, there are two different styles of doing that. One is more, what people call more machine or more FSM, where the output only dependent on my current state, right? Output is only a function of my state element, right? It's isolated from the input. The output is always only depends on my current state. So here, if you look at, here is the combinational logic. It's always depend, the output is always depend on the, only depends on the current state. Whereas the mini machine, where the output, it depends on both my current state and also my input. So that's basically the key part. I mentioned there are two combinational logic. This combinational logic for next state is always the same, right? It's always the current state and the input that will help me to determine where I want to go next, right? So that is always consistent. The key difference for those two styles is really thinking about output, how we process my signal to the downstream component, whether it is just a straightforward way or only dependent on the current state, or it actually a function of both the current state and also the input, right? So this is a key part of the differences between Moore's machine and the mini machine. Why does it matter? What are some of the fundamental differences? Let's take an example to see how you can actually use both way of thinking to express a sequential circuit, but what are some of the implications when you actually use the two ways of thinking. So here, let's try a different FSM. Here, what we want to do is an edge detector. What does it do? So here, the input, we have a bit stream of data. We're receiving 1 bit at a time, so that's our input. And output is a binary option to indicating whether I find an edge or not, right? And in particular, for this edge detector, I want to detect whenever my input bit stream goes from 0 to 1, so this is a rising edge detector, right? So what I want to do is that whenever I see my input go from 0 to 1, I want to let my downstream circuit, oh, here things has changed. It's go from 0 to 1, right? That's the only edge I care, right? So let's see for this element, let's say this is the first bit coming in, and this is a later bit, right? What I want to indicate is that whenever 0 transition to 1, I want to tell my downstream circuit I have seen a transition. Whenever 0 transition to 1, I have seen a transition. It stay like 1, I don't care. If it goes from 1 to 0, I also don't care. I only care about this rising edge detection, right? So this is a particular function that we care for the discussion. So how do we do that? We can certainly implement this as a moral machine. You can think about this done after the class, but for the discussion, we have a way of thinking, an example of implementing this as a moral machine, right? How does it work? We have 3 states. We have 0, we have a change, we have 1 state. Those are the 3 states. We encode it. And now we want to see how my state actually transitions with different output, right? So let's say, remember we have this, let's say, this is my input stream, right? So this is go from here to here, right? So let's say we start from 0, I see another 0, I stay here, right? But if I start, I see another 1, I go to the next state and indicate things has changed. This is a pattern you want to detect, and things have changed. This got to my change state, right? And then after the change, if I see a 1, I go to the 1 stage. If I see a 0, I transition, right? So this is a way of designing a more FSM based on the state transition here, right? So it's a more machine because the output is only dependent on the input. Sorry, output is only dependent on the state, right? If I'm in the change state, I output 1. If I'm not in the change state, I'm either in 0 state or 1 state, I actually output a 0, right? So this is a more machine. Does this make sense? Does this do what we want to do here? Question?
Yeah, so for edge detector in production, would you want the output to be also multiple bits in case it's only one of the bits of the input that goes up?
Is there a case to have the output to be multiple bits?
Yeah, if in the input bits, you might just have only one of the bits go up.
As an edge detector or as a counter, you want to count the number of a number of occurrences that input actually goes up? As an edge detector, is there a case where you want to have a multi-bit output? What that multi-bit output will encode?
Oh, it would just encode which bit of the...
Oh, you want to remember the position of... Oh, yeah, you can also add more functionality, right? It's not only like it transitioned. You also want to tell the downstream circuit this particular bit is transitioned, right? So here you can have an output. You have another output actually outputting which bit. Yeah, that's a fair design. Yeah. Okay. Maybe for this design, any particular reason we have both 0 state and 1 state? Why don't we just, if it's 1, we just go back to the 0 state? Why we have a separate 1 state in this example? Joy?
Then you're not set for like changing. You have to have a 0 before you get to a 1 in order to count it as a change.
Exactly. So if you can actually you want to actually set back to 0, so you can actually catch this pattern, right? If you go back, if you actually do 1, you actually capture this as I just fall back to this one. You actually don't miss the initial 0 condition, and that will actually may lead to a wrong design because you don't actually catch both, right? So it's actually very important you actually have a separate 1 state. So this is a way to actually design this in Moore's machine. We talk about once you have state transition, you can get a symbolic table, you can add encoding to it, and then after that, you can do the Boolean simplification and then get to a hardware here, right? So here, in particular, my output only dependent on my current state, right? So here is my current state. machine. So this is a Moore machine. We can design it. But at the same time, we can actually also design the same as a mini machine, right? So here, things are actually a lot simpler. We have 0 and 1 state. And again, with a mini machine, output is not only associated with state, it's also associated with both the state and the input, right? So if I'm also in the 0 state, I see a 1, my output is 1, right? So I'm transitioning from the state 0 to 1. I get the input 1, my output is also 1, right? So because this is a pattern we like to determine, right? If I'm also already on the 1 state, I get 0, I fall back, and there are different state transition parallel. You can actually do that, all right? You can walk through this to see how this catch the patterns of 0 to 1. This is a much simpler representation of the hardware, and the output instead actually depend on the state. You can only is actually associated with both input and state. And here you can get the state transition graph and a diagram. And here is output. It depends on both the current state and also the input. So now we have two ways of describing the same circuit. Both actually express basically whenever we find an edge, we actually output a 1 to the downstream circuit. Is there any difference between those two implementations?
You have to wait a cycle.
Yeah. For Moore machine, you have to wait a cycle, right? Because you only do the state transition when the clock actually hits, right? So if we actually look at the timing diagram, right? So we have our clock and our input change, right? For the Moore's machine, the only time we actually trigger transition is when state transition, right? When state element changes, and that also we trigger by clock. So the output of Moore is always synchronized with clock. When clock changes, my output changes. Versus mini machine, my output is a function of both clock and input, right? So here, when input changes, actually my clock changes. So it's a faster way of actually see how my output actually react to the input. Nicholas.
Like in industry, how do they usually manage like the volatility of machines, given that like if the input just keeps changing output?
Right, that's a good question, right? So if you look at like the one we will compare all the Moore machine and the mini machine together, right? So we talk about Moore machine is more synchronous, where mini machine is actually asynchronous, right? So mini machine you can actually output change immediately, but there could also be issues because if the input, like for example, for this clock, for this design, right? Let's say the input actually change very late, right before the clock edge. And for a mini machine, like the output also change when input changes here, right? But the output also depends on the clock, right? So when the clock triggered, the output also get updated, right? So the outputs in this scenario, if the input arrives very late, you could just have a very narrow glitch of the output, right? And then the problem is that whether it will be actually caught by the downstream circuit, as it's a very small signals, right? Whether it actually the downstream circuit can actually catch it, right? So that's a very important component. And when you do the design, you typically want to, if you actually intentionally want to design a mini machine, like for example, when you design your forwarding logic in your pipeline or hazard detection in your pipeline, right? So whenever state change and you observe a pattern where the output want to change immediately, you typically don't want that to be on the critical path. You still want to other signals propagate through and your input hopefully change right after the clock. So you have the entire clock cycle to propagate and process that signal, right? So if you want to have a, like forwarding logic, a very good example, you want to detect this is, I want to do some action whenever detect pattern, you want to make sure the input change early enough instead of doing very, very late. And then it's, but for example, Moore's machine is very good for example, your decoder logic, right? I see an instruction, I see this is my opcode, I state my opcode, and that opcode will dictate how I actually interpret other things downstream, right? So that is a very good example of how you want to use Moore's machine. You have a stable current state, and you use a current state to actually determine where things are. But for some of the more dependent things and more like dynamic behaviors, you want to use this kind of more faster way of response so that you can actually catch the patterns there. Does things make sense? The high level mini and the Moore machine? Okay, so with that, just a very quick example. Of those diagrams, let's just quickly spot what are the Moore machines, what are the mini machines. We see, I guess, both a state transition diagram and a little bit more, I guess, the logic, not necessarily gates level, but thinking about circuit diagram there. What are the Moore machines in this? Any guesses? Joy? A and D. So A is Moore machine because the output is encoded in the circle, it's basically associated with the state. And for D, we mentioned this is a combinational logic. It only depends on the current state versus here for output, the combinational logic depends on both the current state and the input, right? So again, this is a very high level way of differentiating Moore's and mini. Both are very commonly used, and you will get to play with that, both of them in your design. Just a quick recap. I guess today we talk about the sequential logic. The key part is we have the memory elements. We think about finite state machine, 3 components. We have registers to store the states, 2 flavor of combinational logic, 1 to compute the next state, the other to compute the output. For Moore and the mini, they are very similar in terms they both need a state element. They both need ways to predict the next state. The key part is how the output, whether output is only depends on the current state or the output depends on both the current state and the input. We talk about more abstract term for this class. Next lecture, we're going to see how you actually implement them in Verilog for both Moore machine and the mini machine. And we'll get started on the RISC-V introduction, so that folks can get started on the pipeline side. With that, good to see everyone. Hope you have a good week. I'm looking forward to seeing you this Thursday.